Ma'am, I hope my slides are visible.
Yes, sir. It's visible, sir. It's visible.
Okay. Okay. Thank you. Yeah. So in this session, we will be focusing on ear biometrics, and I will be particularly discussing a few techniques from the 3D ear biometrics, and these techniques are actually developed by my group. My student Ayappan has worked in this domain, and then has actually written his thesis on 3D ear biometrics. So I will be actually discussing three of the techniques that he has developed. So, so as usual, as we discussed in the last class, last session, we will be having some basic background, and we'll discuss basic background, and then we'll move towards these specific techniques. So, whenever we have availability of multiple biometrics, and we are choosing ear as one of the biometrics for developing a system, the question comes, why ear? So we need to actually find out what are the advantages we are using, we are getting when we are using the ear as a biometric. So one of the good thing about the ear is that this is a contactless biometric. That means to capture the data, you don't need to be you don't need to go to the close to the person. It can be captured from a distance, and also it is non-intrusive. Right? So you don't need user cooperation for this. And also it is found that ear is robust to age, beautifiers, and outward appearances. So as you know, so whenever we have ear in discussion, we always compare it with the face, and the reason is that the way we capture the face and the ear, the procedure is same. Like by using a normal CCD camera, you can capture face, and with the same, you can capture the ear also. So the question comes, why do we need ear? Why can't we just work with the face? So there are certain advantages that actually we have with the ear, and that are not there with the face. So like what you see here is, if you compare with the face does not carry all these characteristics. For example, over the age, the face changes, but the ear is quite robust to this. Similarly, when you are applying cream or other things, the face gives a different look, but you don't have any such thing with the ear. And similarly about the outward appearances, the ear is very less affected. Also, we find that the ears are quite distinctive, and I think this is the basic requirement. If the ears are not distinctive, we can't use them for the biometric purpose. So they are distinct and can be used to compare different individuals. And it is also found that you know that face is very similar for the twins, but it is found that there's a study in this paper. You can just go through it. It shows that the features are actually features of the ears are distinct for the twins, right? So this is again, you say that there's a good thing about ear when you compare it with the face. And many times ear is not used for recognizing a person alone. It is actually used along with certain other biometric modalities, and a very common thing with which it is used is the face, because as I said, the face and ear, they can be captured both using the same kind of device. So ear sometimes becomes a supplement. It is used with some other modalities to improve the performance. So all these facts that you see here, they are actually saying or telling us that ear can be a good biometrics. Now, when you are performing the ear recognition or biometric recognition with the help of ear, you can perform this in two ways. One is in the 2D and another in the 3D. In case of 2D, you are actually using the 2D images that are captured by the 2D camera that we have, like CCD camera or the camera that you have in your mobile phone and all that. And if you want to use 3D images for the recognition, then you need actually specific hardware, and with the help of that hardware, you need to actually capture the 3D data of the ear, and then you can actually make use of it. So in case of 2D, you have 2D images, it's simple to capture. But in case of 3D ear biometrics, you need 3D images, 3D data of the ear, and for that you need a sophisticated hardware. Now, here I will be talking about three techniques which are from the domain of 3D ear. Now, comparatively, 3D, as I said, performing 3D ear recognition is challenging as compared to 2D image, 2D images based ear recognition. And the reason is that here you have, first of all, the procedure to get the data is simple. You can use any readily available camera for capturing the 2D data, but that is not true for the 3D data. You need sophisticated equipment for capturing the 3D data. So it's a bit difficult to capture the images. And secondly, if you compare the size of the data in case of 2D and 3D, you find that these 3D files are uh, heavier or bulkier compared to the 2D images. Okay. So since it is costly to work with the 2D images, why, sorry, with the 3D images or with the 3D year, why do we actually need to go for the 3D year? So there are some advantages that we get when we are using the 3D data, and one of the advantages is that the 3D data is invariant to illumination. Right? In 2D case, as you see here, different ER images have different illumination. If you have captured the data in a dark place, you will have poorly illuminated images. But if you have captured them in the in open space, then maybe they are they are too much illuminated, right? So the illumination problem is inherently there with the 2D images. Similarly, you have the pose variations. Like if you have captured a particular pose and you are trying to recognize the person from a different pose, you won't be able to do that because they both will not, those two images will not match because of the obvious reasons, right? So pose issues are there with the 2D data, they are not with the 3D data, right? Similarly, this illumination is also not with the 3D data. And scaling is another factor. When you are capturing your image in 2D domain, uh, the the size of the image that you are getting actually depends on how close or far you are from the object. And depending upon that, you will get the image. But in case of 3D, that is not the case. Whenever you are capturing any object in 3D, you are actually getting the true dimensions of the object. So depending upon the size of the object, your size of the you will get the size of the data that you get from the device, right? So there is no scaling issue in case of 3D EL. So because of these advantages, we basically go for the 3D ear recognition. Now, 3D ear recognition, there are two ways popularly used for comparing 3D ears. One is that, and if you have some background, you might be knowing that this 3D data is actually collection of some points. So when you are capturing any object with the help of these 3D sensors, what we basically do, we virtually assume that there are some points on the surface of the object, and then we try to extract the coordinates of those points, and with the help of the coordinates of those points, we represent the object. So any 3D data, you can say in simple sense that this is collection of some endpoints where every point is defined in three-dimensional space, x, y, z, having x, y, z values. Right? So very often it is referred as point cloud. So 3D representation is actually in terms of point cloud. Uh, you have set of points which are actually defining the object. So when we do the ear recognition, any recognition is going to deal with matching of the two samples, right? So here also you have two 3D samples, one sample, let's say this one, and the other sample this one, and you want to you want to find out how similar they are. So the one way is that you take the sample and register with this sample, and then see what is the registration error, right? How closely you can actually register these samples with each other, and the error will tell you how similar they are. If you have very less registration error, that means they both are similar, very similar, and if you have high registration error, then that basically means that those samples that you are matching or comparing are not similar, right? So this is one approach where the registration is used. So here you just need the 2 point clouds, and then you need to just register them with each other to find out how similar they are. And there's another approach that I will be discussing that is based on the feature descriptor, where we extract some set of features from these 3D AR images and then match those features. Okay. So let us first discuss about the registration-based approaches. So whenever we are registering to 3D point clouds, we have two types of registrations. One is, so this is the way we actually register one point cloud with the other point cloud. We are basically trying to align with the other. So we are actually making translation and rotations on one data or one point cloud data to get it registered with the other data. Right? So like you see here in the other example, you have uh, two samples. Now, if you compare the registration that you saw here and the registration that you are going to have here, uh, here you see that these shapes that you are having are rigid. And sometimes you may have, I mean, so when you are registering one sample with another sample, you are maintaining its geometric shapes, geometric features, right? So relative distance between the points will actually always remain same. But if you see when you are trying to capture this with this, you are basically deforming one object so that it matches with the other object, right? And then based on that, you are performing the registration. So we can have when you are performing this registration, this kind of registration, it could be rigid or it could be non-rigid, right? So sometimes we may require non-rigid registration as you're seeing here. But in our case, when we are dealing with the biometrics, we don't want to change the data. We don't manipulate with the data. So we are also always going to be using the rigid uh, registration. So we are going to assume that the shapes that we are matching, they are rigid. They cannot be deformed. Okay. So relative distance, as I said, the relative distance between the 2 points that you have there uh, in uh, in these samples that will remain same when you are performing the registration. But here, in the other case, it can change. Okay. So let us see how we are performing this rigid alignment. So for this, we are basically, so we have two shapes as you see here, shape one, and all these shapes are represented in 3D, though these pictures you see here are in 2D, but assume that they are represented in 3D. That means they are represented in terms of collection of uh, 3D points. Okay. So you have shape one and shape two. You are basically trying to align these two shapes. So first, what you do, you basically try to get the point correspondences. You have one sample here and another sample here. You are trying to find out the point correspondences between these two. And then once these point correspondences are available, you do some kind of transformation in terms of rotation and translation, and then try to align them. So here you have, let's say, P1, P2, P3, P4, P5 points in one sample, and then Q1, Q2, Q3, Q4, and Q5 points in another sample. And then based on this correspondence, you are trying to align them. So the first thing is when you are performing this region alignment for any given set of shapes that you are trying to match from one shape, you have to find out the point correspondences in the other shape. And in this point, when you are finding the uh, uh, correspondences, there could be different criterion. For example, here what we are doing is based on the nearest point. So for every point, you find out what is the nearest point in the other one, and then uh, you see that those are the corresponding points. So once the point correspondences are known, there is a set procedure which can be actually used to uh, used to align these point clouds or these set of points with the help of this registration procedure. Okay, so in this procedure, there are two things actually involved. If you see here, translation and rotation. So for example, you are matching this, you have set of points represented as PI and another set of points represented as QI, and you are trying to align them. So you have to first find out the point correspondences, and once that is established, then you will be performing some kind of translation so that they come close to each other, and then performing some kind of rotation so that they align with each other well. So to accomplish this, we have certain standard techniques. For example, this alignment can be done with the help of PCA, or it can be done with the help of SPD, or there is a very robust technique which is often used is the iterative point iterative closest point matching technique. It can be used for aligning the procedures, aligning the point sets. So let us see what is the problem with the how we do this in with the help of PCA, and then what are the limitations, and why do we need SVD or ICP based registration. So in case of PCA, what do you do if you have some background with the help of PCA for any given data distribution? You can find out directions in the data which are where the data has the highest variance, or the orthogonal direction in which the data has next highest variance, and so on. So for any given data, you can actually compute for any given data set that you see here, you can compute these two axes, right? You do some kind of eigen analysis of the data, and then these axes are determined with the help of eigenvectors. So for this data distribution, you can get these axes with the help of eigenvectors. For this data, you can get the axes with the help of this uh, uh, I mean, with the help of the analysis of this data, you can get these axes using the eigen analysis, and then to align them, it's very simple to rotate them in such a way that the both axes actually get merged with each other, and that gives the perfect alignment. Some cases it is possible. For example, here you see we are getting a very good alignment, but sometimes, particularly in case of noisy data, this technique is not very not, does not perform very well. For example, you see when you have little noise here, you see that these axes that we are computing, they will be affected. So in place of having the axis like this and this here, because of this noise, you will see that they will be little shifted, and you will get the the axis here. And if you are aligning these two data sets with the help of these axes that we are getting here, you see that the alignment is not perfect. So you can say that the PCA is affected by the noise. And second, also sometimes you may find that the the directions that are given by the eigen analysis or with the by the PCA, they are not unique. For example, here, though the shapes are quite similar, but in this case you are getting these axes, two axes like this, but and here you are getting these two axes like this. Now, when you are actually aligning them with the help of these two axes that you are getting, your actually data gets aligned like this, which is you can say not correct, and you see that the PCA fails here. And so that's where I mean you can use the SVD. What SVD does, it doesn't give. So in here you see that the alignment happens in one go, right? You directly you have two sets, you analyze them, you get the features in these axes, and then just align these axes in one go. But in case of SVD, this is like a iterative procedure. So it is considered to be quite robust as compared to PCA. And in case of in ICP, actually we use the combination of PCA and SVD. So with the help of PCA, we are able to translate the translate one point close to the other one, and then with the help of SVD, iteratively we align uh, the 2 point sets. So here you see the transform or the translation is happening because of the PCA, and then with the help of SVD, the iterative alignment is happening. So in ICP, this step 2 is repeated again and again, and every step or every alignment when we are doing, it gives you a registration error. So let's say if you are iteratively performing the alignment, then you can keep performing it till you get the uh, error within certain limits, or you have, let's say, exceeded the number of iterations that you fixed. So based on some terminating conditions, you can keep doing this procedure. Okay. So let us understand that with the help of these examples. Always, whenever we are talking about matching of two sets of 3D point sets, you use these names data and model, and where normally data will be moving and the model will be fixed. So for matching, as I explained earlier, what you have to do when you have to match these two, let's say 3D shapes or 3D data representations, you have to first locate the points in that, and then you have to find out the point correspondences. So you have, let's say, these are set of points, and then you have the point correspondences uh, with respect to this data. Then you have to use these correspondences and you have to align them. Right? So you have one set of points here now, you have another set of points here, and then you have to align them. Now model is fixed, model is fixed here, and the data is moving so that it gets aligned with the model. So first, you see this movement is happening because of the PCA, direct translation because of the use of PCA, and then iteratively the IC, the SBD is used to align these two models as much as possible. Okay, so finally you get the aligned sets, and then you can actually compute the registration error, and that gives you how well these 2 points are aligned. If these point sets are the alignment procedure gives you very less error, that means the alignment is really good, and then the two shapes that you align are matching to each other. And if the error is more, then obviously it shows that they are not matching it. Okay. In data, we have different types of representations. Though we are saying that these are different representations for 3D here, but this is true in general. Whether you are whatever you are representing in 3D, that can be represented in terms of these different ways. Like in point cloud, you are representing the surface or the geometry of the object with the help of some set of points. In case of mesh, you actually so this is generated from the point cloud. So you take the point cloud representation, and then for every point you find out the neighboring points around that point, and then you create a mesh kind of structure, and that gives you the mesh structure. This is like a rendered mesh, so you can visualize. I think if you are able to see the triangles here, and sometimes we uh, create the voxel representation, and voxel representation is usually divides, it considers that the 3D object is a volume, and then that volume is actually represented with the help of a unit cube. So we try to see how many unit cubes can fit inside the volume of the object, and then we represent every uh, cube that is fitting there in terms of XYZ coordinates. So here in our discussion, we will be following this point cloud format, which is the most raw data that you can say uh, that is obtained from sensor. Right? These are a few examples uh, for the 3D data. This is for the all are the years from UND J2 database. At Itindor also we have year database, and in this database actually consists of 2D and 2D as well as the 3D year data. These are two samples from the database. This is the sensor that we are using for capturing the 3D data. This is called the Artec EVA 3D scanner, and for collecting the 3D database, for collecting the 3D data, you have to actually take this sensor, take this camera, and then you have to move all around the object. So this is the procedure we have used to capture the complete profile scan of the person. So this is the person sitting here, and then the camera is moving from here to capture all the possible poses for the person. These are some working pictures. This database also has 2D face images. We are not discussing any technique based on 2D face images, but the database contains the 2D images as well. These are few samples from the database. It also has 3D face along with the 3D ear.
Hello, sir.
Yes, ma'am.
Does this database it captures both face and ears together, or and then segregates, or ear only exclusively separate? I mean, as the
So,
data.
yeah, so here actually we have captured both simultaneously.
Mm.
So as you see, this goes from this side to this side, so it captures face and ear both.
Okay,
But
and then
obviously, yeah, no, but actually in ear, I mean, since you have some occluded parts, you need to pay more attention there when you are scanning that.
correct, sir. Okay. No, you like as you said, the database consists both 2D image and 3D also in the
Yeah.
same.
Yeah, but actually those 2D images are captured using the different sensor, not from this sensor.
Okay, okay, sir. Okay, okay.
Yes,
So
that is,
here, using this sensor, we capture from one ear to the other ear
yeah, only
along the
3D.
face.
Yes, face and ear in 3D. It doesn't
Okay,
give the
sir.
data in 2D.
Okay, sir. Okay, sir.
Yeah. There are some sensors actually which can capture the 3D and 2D, I mean, simultaneously, but this device doesn't do that. So if you see, I mean, if you just see the data of this UND J2 database, so there they have the 3D pictures and along with that they have the registered 2D images. And that is actually being captured simultaneously. So 2D picture and the 3D both are captured simultaneously. But here we have done that separately because this device does not have that capability. Yeah, so these are a few sample images I said. This is the list of some popular databases in the domain of year. Uh, these few examples are for the 2D and I mean if you just see these columns, it gives you the details about the type of data that you have. Like in our case, we have 659 subjects and total 5272 images captured, and then we have captured both the sides. Uh, and Occlusion is quite mild in our case. The subjects that we have taken are from both genders, and then obviously the ethnicity is Asian because we have captured the data in our campus only. Okay. These are few popular 3D databases. In our case, we have captured the data. We wanted to also do the study of age invariant nature of the face, age invariant nature of the ear. So we have captured the data in three phases, and there was a gap of I think around 1 year in these phases. So in phase one, there were 188 samples captured. In phase two, 176 samples were captured, and then in phase three, 188 samples were captured. And there were some actually some samples which were common in all these three. Right, I don't have that detail right now, but for the study of the age invariant nature of the ear, we wanted some samples which are actually common in all these three, and those were only used for the study. Okay. So uh, now let us move towards the matching of 3D ER or any 3D object with the help of descriptor. So in case of descriptor, what we do, like we have seen in case of registration-based approaches, you have two samples, 2 point clouds, and then you just register them with each other and then compute the error of the registration and use that as matching score. Now, what we do here, so in case of the descriptor based approaches, first we have to compute a descriptor and the matching is performed based on the descriptor of the year. So here we have, let's say, one example, one year, and so we need to compute its descriptor. And then in the database also for different years, you have the descriptors being stored, and the descriptor for this year need to be matched with the descriptors of the other years that are stored in the database to establish the identity. Okay. So first here is that we need a descriptor from the sample 3D year that we have. We need to actually compute the descriptor of it, and then only we will be able to compute the uh, we'll be able to compute the match score. And these descriptors are going to be often a vector. So when you are comparing two vectors, then you can compare them by comparing the distance. So you can use some distance measure, and then based on that you can uh, compare how similar those two descriptor vectors are. So we have some interest in this domain because these methods are quite cheap and also quite up to quite extent robust. We are saying quite cheap in terms of the computational cost. So when you are registering the two samples directly, that requires actually huge amount of time. But when you are capturing the descriptors from the 3D samples and then matching them, this matching is really very fast. Okay. So this is the general outline of any 3D descriptor based matching. So you have initially the point cloud, then you extract some feature points from it, and then those feature points are actually described with the help of a vector. So that's how you get the descriptor vectors for those 3D samples. And similarly, so this happens when you are, let's say, registering a person with the system. The same is done at the time of testing. You have 3D point cloud, then from there you extract the feature points, and then every feature point is described with the help of a descriptor vector, and then the matching is actually performed in this descriptor domain. So the descriptor vectors are being matched to compute the score, and then that score is used in matching in taking the decision. If the score is more than threshold, you say that the matching is successful, otherwise it is not successful. So this is the common procedure which is used in any domain where you are performing the matching based on the descriptors. Yeah, I think we will just skip this. Yeah, so these are some popular descriptors which have been actually proposed in the domain of 3D data. These descriptors are not particularly for the 3D ear, they are generic descriptors. That means for any object which is represented in 3D, these descriptors can be used, and they can be used for matching. But later I'll show that these descriptors, these generic descriptors are not very useful in matching the biometric data. These descriptors are only useful when you are matching the objects which are from two different classes. When two different classes, I mean, when the classes are very distinct. For example, you are matching, let's say, a chair represented in 3D with the table that is represented in 3D, like that. But in case of biometric data, the ear, I mean, if you see the geometry of that, though you will find a difference, but overall, every ear is similar, right? So if you have such similar classes, these generic descriptors are not very useful, and that is why we have proposed our own descriptor, and that works quite well for comparing 3D years. But these are good descriptors. Actually, if you're interested, you can go through these descriptors to get the basics. And I mean, if you go through them, you'll find that there are limitations, and then maybe you get the idea to develop your own better descriptor. So I just skip this list. Now I'm going to discuss these three techniques which are used for 3D ear recognition. First one is the ear recognition using global and local features, and another is ear recognition in 3D using 2D curvilinear features, and then the next is geometric statistics based descriptor for 3D ear recognition. This is the last one. I mean, this is the most efficient one that we have developed and gives the best performance. Okay. So in the first technique, we are going to discuss the use of global and local features. So when we are capturing the global feature of any object, we are able to get its global appearance, and when you are capturing the local features, we are able to get the local details. Now, in some cases, the local features are very helpful. For example, if the object is affected by, let's say, occlusion, or only partial data is available, or the data is noisy, in those cases, we see that the local descriptors or local features are more useful, right? Because in case of partial matching, if you are computing a global feature, if you have a full object and you have a partial object, obviously the two sets of features that you are going to extract from these two samples are going to be very different. But in case of local features, this part and this part might be same in both the cases. So all the features that you're extracting from uh, this sample here and this sample here, they could match. So it's in these scenarios, like in case of partial matching, or in case of occlusion, or in case of noisy images, local features are very useful. So here we are actually trying to make use of both global and local features to perform the recognition. So this is technique, as I said, this technique is based on global and local features. So here we'll see how we are getting the local and global features. So to compute the global feature, here we are actually making use of a technique called local sphere geometry pattern. So what it does, it considers a point in the point cloud, and then also it considers, and around that point it considers concentric circles, and it also considers some neighboring concentric circles around this point, and then based on it computes some value for every representation that you have here, and then it compares that representation with the the same representation that you get from the center concentric circles, and then based on that comparison, it assigns a binary value. So as you see here, you have eight surrounding circles, so you get eight values, and with the help of those eight values, and these values are 0 and 1, wherever the value that we are matching with respect to the center and uh, the the other surrounding circles, if the value is satisfying the criteria, this value is 1, otherwise 0. So basically, the outcome of for any point, the outcome here is a set of eight bits, and those eight bits, if you just represent, they give you one value. So in an ear image, if you have let's say n cross n image, for every point you do this analysis and then get a value, and that value, if you are representing it as a grayscale, then your image can be converted to a two-dimensional grayscale image, as you see here. Right? So this whole thing gives you the global information about the face. Now, what we further do, we divide that entire space, entire image that we got in the previous slide, into some grids, and then every grid is actually for every grid we are computing the histogram of it, and then concatenating that entire uh, set of histograms to get a global large feature vector. So here, let's say this was n cross n uh, grid. So here we're getting n square histograms, and then all those n square histograms are combined to get the global feature vector. In terms of performance, it has the most important performance measure is the EER, the equal error rate. This rate basically it is, so you compute the FAR and FRR, false acceptance and false rejection, and if you plot the false acceptance and false rejection with respect to the threshold, you see that when you are increasing the threshold, matching threshold, the the one increases and the other decreases, right? So that because they have the contrasting nature. So there's a point where these two curves actually meet. That point you have both these errors same. FAR is equal to FRR. So the false rejection and false acceptance is the same, and that is the most ideal situation. So whenever we are comparing any biometric system, or when we are comparing its performance, we actually compare with the help of EER. So for this system, we are getting the EER as 1.56%. And this is the comparison with other existing techniques, and we actually see that compared to other techniques, this has quite good performance. There was one technique, this one, where the performance is a bit better than our technique, but here you see that they are not only working with the 3D images, they are also using the co-registered 2D images for performing the recognition. The other technique that we are going to discuss is this ear recognition in 3D using 2D curvilinear features. So here, in this case, we are actually making use of 2D and 3D data both for the ear. Uh, and this is a technique which is based on key point detection and description. So here we are uh, going to perform the matching based on the descriptors. And as you know, if you want to the 3D data is given and you want to get a descriptor vectors, so you have to first identify some salient feature points in that, and then you have to describe those points with the help of these descriptor vectors. So uh, this is the overall procedure of obtaining the salient points and then uh, computing the descriptor vector for them. So here, as I said, we are making use of 2D and 3D images both. And these 2D and 3D images are co-registered, which basically mean uh, if you see the portion of the data that is being captured by the 2D and 3D, that is exactly same. Only one representation is in 2D and other is in 3D. So here we are in this technique, we are using 2D technique, 2D images for computing the salient points, and then uh, those salient points, since these two images are registered, so whatever the salient points we are getting in 2D, they are actually mapped to 3D, and then in 3D, corresponding to those points, descriptor vectors are generated. We are interested in actually computing these salient points in 2D because uh, the 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 domain of salient point extraction in 2D is quite mature. So since these uh, two sets of images that we are going to use, 2D and 3D, they are registered, we can extract some information in 2D and very easily map to the 3D. And that is why just to take the just to just because we had this kind of mapping between the 2D and 3D data, we could actually use the detection in 2D and then description of those features in 3D. So what we do, this is the procedure. So this is we have the input image. From that input image, we get some intermediate processed image, and then in that processed image, we are detecting some curvilinear features. And then those curvilinear features, all the points which are defining these curvilinear features, they tell that they give the salient points, and those salient points are mapped in 3D, and corresponding to those points, the descriptor matrix or the descriptor vectors are generated. Right? And the same thing is done for the probe and gallery images, and then the matching is performed. So here, one thing you can notice that uh, the the matching that we are performing is with the help of ICP. That means we are registering the 2-point clouds. But when we are registering these 2-point clouds, whenever you are performing any registration between the 2-point clouds, you need to also you need to know the point correspondences. So these descriptor vectors we are using in finding out the point correspondences. So I think in the later slide, I have more details so that it will be more clear there. Here you see an example of 2D image and 2D ear image, and it's registered 3D ear image. So you see here, this is the 2D ear image, and exactly the same thing is being represented here in 3D. If you just I mean, compare the portion of the ear here and the portion of the ear and the appearance of the ear, you see that it's exactly same. Only the difference is that here the data is in 3D and here the data is in 2D. This is the, for example, this is the rotated or the different view of the same ear. So from here you can get the feel of 3D. So the steps that are involved in this procedure are these. There are two steps. One is the key point detection and then the key point description. What we do in case of key point detection, we are actually using the 2D images, and then from those 2D images, we are trying to find out salient points. And those salient points are mapped to the 3D, and then they are corresponding to those points, the description vector and description vectors are obtained. So for finding out the 2D salient points, actually we're using we are computing the curvilinear features, and for computing the curvilinear features, we are using these filters. So this is the mathematical definition of the filters, and these filters, I mean, we are using a set of filters, and these filters look something like this, as you see here. And those filters are actually applied on the ear image. You have, let's say, 4 or 5 filters. All of them are applied on the ear image, so you get and 4 or 5 filtered images, and then by aggregating the information, you get the final image, and from that final image, the curvilinear features are generated. So whatever you see in the final image is basically highlighting those areas where the curvilinear features are there, which basically, in some sense, telling you the places where the more curvature is there. So this image is giving you thick regions. So to get the thin regions from this thick region, we are performing the thinning operation. Is a morphological operation called thinning that we are performing to get a thinned image, and that procedure gives us the 1 pixel wide areas. And when you map them on the 2D image, the mapping looks something like this. So all the red point that you see here, they all are the feature points. They have been just superimposed on the 2D image to uh, to get better visualization. Right? So what we do from the 2D image, we extract these points, and then these salient points are mapped to the 3D. Since we have 2D and 3D images registered with each other, this mapping is possible. If you don't have this kind of registered images, then this technique is actually not applicable. So this is the overlapping of those salient points on the 2D image, and here you see the corresponding to these salient points, the 3D points highlighted in the 3D domain. So when we are performing the matching, we are actually registering the 2 point clouds. Now, when you are registering the 2 point clouds, as I just said, you need the point correspondences. So you have one set of point cloud here and a set of point cloud here. Now you need to establish the point correspondences. So you take a point here, and then now trying to find out which point in this set of points matches to this point. So to find out whether this particular point, let's say, matches to this point or not, we are comparing their descriptor vector. So this point also had a n-dimensional descriptor vector. This point also has a n-dimensional descriptor vector. Now, if you compare the distance between them and you find that the distance is very less, then you can say that this point is corresponding to this point here. Right? So like that, you have, let's say, n points here and m points here corresponding to every point here. A corresponding matching point is obtained in the other set, and then ICP registration is applied to compute the registration score. Okay, so this is what exactly happens. From the 2D, you get the 2D salient points. Then you are mapping them to 3D. Here, the other sample that you have in 2D, from that you are computing the 2D salient points. Then they are mapped to the corresponding 3D data, and then the point correspondences are obtained between these 2 point sets, and then you are applying the ICP registration to match them. So in terms of the performance, this technique has given slightly better performance as compared to the previous one. It says equal error rate as 1.553, which is slightly less than the one that we have earlier. But this technique has a limitation that this can be only used when 2D and 3D registered samples are available. If only we have 3D, then we can make use of it. Okay. We also tested this for the noisy cases and also for some uh, occlusion cases, and we found that this has worked quite well. Obviously, when the noise is being increased or when the occlusion is being increased, the performance is degrading. But uh, up to certain level of noise or occlusion, it has given acceptable performance. Okay, this is the comparison. So here it has 1.53 error rate, and again, I think this is less than this particular technique. But in this case, actually, this technique fails when the pose variations are there because it is not able to handle the pose changes. But uh, this can handle the pose changes because there is no effect of change of pose in this particular case because we are matching it to 3D data with the help of ICP. And there are some actually there are certain things that are I mean, if you just go and read the details of this technique, there are certain things that they are extracting from the ear based on its pose. So if the pose changes, I mean, you face difficulty in locating uh, uh, those features or those portions from the ear for recognition. So they are actually they are the technique that they are adopting for computing different kinds of things from the 2D sample as well from the 3D sample. That is, they are actually dependent on the ports. But here we don't have anything that is dependent on the ports. So this is we can say that it is invariant to pose. It doesn't have any effect uh, with respect to pose. Yeah, this is the last one, this last technique that we are going to discuss here, and this has actually obtained the best performance out of these three techniques uh, that we have developed in this domain. So this is based on uh, a feature descriptor. As the name suggests, it says the geometric statistics based descriptor for 3D here. So this actually proposes a way to compute the uh, local descriptor vectors for 3D here and then make use of them for the recognition. So initially, I highlighted that there are a couple of generalized 3D descriptors available in the literature, but these descriptors are not very well suit for the comparison of objects like 3D ear or 3D face. Like when we are using those descriptors for the biometrics, they don't perform well, and the reason is that those descriptors are not not very efficient in distinguishing the two class of samples which are very similar, right? And but in case of biometrics, as I highlighted, whatever biometric data we are capturing for two persons, it is in by and large it has very similar things. Like the two faces have both the faces have nose, eyes, and all that. Similarly, in the ear also, the structure is quite similar. So these generalized descriptors are actually not uh, very useful for comparing the data in biometrics, and that is why we have proposed this descriptor, and this has performed quite well. Uh, so this technique is also going to have the two stages. One is the key point detection, where we are locating some salient points in the 3D data, and then the second stage will be the description stage, where every point will be described with the help of a feature vector. Okay. So this is the procedure for computing the key point. So here we are, I mean, considering all the points that are there in the data, and then considering their surroundings, and then analyzing the surroundings with the help of eigen analysis. And based on since this is a three-dimensional data, we'll get three eigenvectors and three eigenvalues. So by analyzing those eigenvalues, we are actually detecting whether that particular point is a candidate for the key point or not. So wherever these two conditions are satisfied, we say that the point is a candidate for the key point. Otherwise, we reject that. So all the black point that you see here, they have satisfied these two conditions, and they are marked as the key point here. Right? This is another uh, example for the key point results. Now, once the key points are detected, then we have to actually describe them. Whenever we are doing the key point description, whether it's in 2D or 3D, it is always based on the neighborhood. So when we are, let's say, trying to find out a descriptor vector for a key point, what do you have to do? We have to first take a neighborhood around the point, and then we have to describe that neighborhood. And with the help of the description that we are getting by analyzing the neighborhood, we get the descriptor vector. So the same procedure is going to be analyzed here. And just to reiterate, these descriptor vectors are going to be obtained for only key points, or the unique point that we have detected. So that is why in the first step, we are detecting these unique points, and then for them, we are analyzing the neighborhood, and then uh, describing and or getting a descriptor vector uh, for them. Let us understand what is the procedure of getting the uh, descriptor vector for these key points. I already told you how to get the key points. So for the key points, we are analyzing all the data points that are available in the sample, and for every point we are checking whether this condition is satisfied or not. Wherever this condition is satisfied, those points are marked as the key point. So if let's say in your data you had 1,000 points, and only let's say 50 points are marked as the key points, then this description is being done only for those 50 key points. Okay. So now let us see how the description is being generated for those key points. So this has multiple steps. So what we do in the case of first step, so here we consider uh, a key point, and then around that key point we consider the concentric circuits, or maybe you can say concentric spheres. And we try to see how many points are falling in those concentric spheres. So this is I mean, this is one example. So you have, let us say, you have considered a point, and around that you have considered these spheres of different radii, and then you have computed the points that are falling in that. So you will get some structure like this, right? So if you let's say consider this is your x plane and this is y plane, then you can actually create a histogram uh, out of the projection that you have here. So these histograms that you see here, they are basically showing bins where every bin is identified by its x and y location. So it's something like this. This is the xy plane, and this xy plane is divided into grids. Okay? And those grids are being represented here. And at every grid is considered a bin. Every grid cell is considered a bin, and the value that you are going to put this in this bin is equal to the number of points that are falling in that bin. So that way you have different these histograms uh, for the for these points. And then from these histograms, we are actually extracting the segment moments. For all these images, from all these images, we are extracting segment moments. We are using whose segment moments. We are, I mean, whose gives the, I mean, whose proposed segment moments, but we are not using all of them because some of them are very prone to susceptible to noise. So we are using only five values, five whose moments. And from every image, we get these five whose moments, and then we concatenate them to get uh, this vector. Okay. So this is one vector that we are getting with the help of projection of the points in the concentric spheres that we are considering. Same way we are here. The procedure is quite similar, but in this case uh, we are considering the normals of those points. So normal is a vector. So for every vector, you can find out the angle that it makes with respect to, let's say, certain axis. So you for all those angles, you can directly create the histogram. So here you have the histograms of all those angles, and from that you are concatenating these three histograms, uh, and then you are getting the concatenated vector. So in the second step, again, you are getting a vector, but that is obtained by analyzing the orientation of the normals. Right? In the previous case, we were you can say in some sense we were trying to uh, I mean represent the location of the point. Now here we are trying to represent the orientation of all those points. So points would be same. I mean, the number of points that you will see here falling within certain spheres uh, might be same. And in fact, this would be same because we are considering the same kind of spheres, concentric spheres with the same radius. So we get another set of uh, values from here. And then further we generate another set of features that are based on the sign distances of these points. So we consider a plane, let's say there is a plane P, there's a point P here, and then with respect to its normal, there is a plane which is which is like this. So here, whatever the neighboring points are there with respect to this point P in your data, those points are actually projected on this plane. So some of the points might be on one side of the one side of the plane, other side, other could be in the other side of the plane. So we are using these sign distances to uh, extract the unique features for this point, center point P. Okay. So all these three features that we are getting in these three steps, all these, I mean, they are these all features are actually here, whatever the distance we are getting, or before whatever we have got, that all is represented in terms of histograms, and all these histograms are concatenated to to get a combined vector, descriptor vector. And now remember, all these three things that we have computed, they all are with respect to a particular point. You can say a particular salient point. So the vector, this big vector that we are getting at the end here, is with respect to this salient point. So that is like the description for this particular point. And the same procedure actually need to be repeated for all the salient points that we have got. So let's say we have 50 points, 50 salient points I mean 57 salient points located in the 3D data. So that for all those 50 points, this procedure need to be repeated to get the descriptor vectors. And one more thing we need to take care here is that when we are combining the histograms of different quantities, as you see here, these histograms need to be properly scaled down. So we need to combine the normalized histogram because they are representing different kind of I mean properties or the values. So they need to be first scaled down. They need to be first normalized before combining them with each other. Okay, so that we basically perform normalization and then we combine them. And in this case, we have obtained the best performance, which is ER equal to 1.50. So with this, I think I have reached the end of this presentation. So let us conclude this. So what we have seen in this session is that 3D ear recognition can be a potential biometric trait for human recognition, and this is because of certain reasons. Uh, One of the reasons is that this is robust to illumination and contrast. It can be very easily clubbed with many other biometrics, and then we can develop a multi-model system. And also we see that when you compare to, let's say, face, the ear does not have this aging issues. So since this remains fixed, remains same over the age of the person, so this can be easily easily used overcoming the aging issue. Okay. There are some future directions that we can have in the domain of 3D ear recognition. So one of the tasks that can be taken is the automatic ear detection in the domain of 3D. So mostly the techniques that are available for 3D ear detection, they are based on they are based on use of co-registered 2D images. But if you can have a technique which can be directly applied on 3D, that can save a lot of time. Also, the though it is considered that the age that the ear is quite consistent over the age of the person, but we don't have very rigorous experimental analysis in this. So, for example, whatever analysis we have done, that has just spanned over 3 years. But 3 years is could be a very less time for this kind of study. So, if we can have a big or large database for this, which is captured over, let's say, 5 to 10 years, then with more confidence, actually, we can establish whether the year is consistent over the age or not. Okay. We can also study the inheritance effect or the effect of inheritance on the ear recognition. Uh, we can also extend the deep learning techniques that are available in the literature for 3D eye recognition, right? Uh, in terms of the deep learning, we see that there are very few techniques available for 3D for handling, not for the 3D ear recognition, for in general for handling the 3D data. So this could be another domain where we can think of doing something. Yeah. So with this, I conclude my session. Thank you very much. Again, if you have any question, we can discuss now or
Yes, sir. A
yes, ma'am.
couple of questions from participants, please. This is the interactive session.
Yeah, ma'am. Yes, ma'am. Please go ahead.
Good evening, sir.
Yes, yes, madam. Please go ahead.
Yeah. When it comes to that ear biometric, we are considering the features in terms of geometrical extractions, or else can we extract some biomedical informations again, something like st- you know uh, biological structure of that ear apart from geometrical uh, feature extraction.
I mean, like, can you tell me what do you mean by biological features? So, are you referring to the inheritance kind of
For
thing?
example, no, when it comes to eye face recognition, iris will be that biological term. Instead of having only the shape and then nose, distance, eyebrow structure, and all. like that, do you have any idea with respect to ear where we can go with that genetical, not genetical features to
Yeah,
identify
so
genetical features?
yeah, so actually there is no such a study. So that's in the last point that I said. There could be some study where we can study the inheritance.
Hmm?
Uh, Other, I think since we are dealing with the appearance, we cannot,
Hmm.
I mean, detect any very, you can say, good biological feature. But I think based on pattern only we can establish certain things. But as such, there is no analysis.
Hmm. Okay, thank you, sir. Thank you, sir.
Any other questions? So can you give out one or two applications where they have considered ear as the best trait for recognition, sir?
Yeah, so
Like we have seen face, iris, and all so many applications, and here I have not seen so many applications.
yes, yes. Yeah, so actually that's a very good and very common doubt everybody has that where is it really used? So, as far as the, practical use is concerned, there are actually other biometrics like face and other similar things which can be easily used. So, as far as the market is concerned, I think most of the market is captured by face, fingerprint, and iris, all that. But now we see that there are certain applications where people have made use of even ear for recognition. So now there are some applications. I mean, if you just browse through the net, you can actually get those applications where people have developed, for example, app where ear can be used for recognizing a person. But but if you are concerned about the place where only ear can be used, but not the face, maybe uh, I think wherever ear can be used, face can be used. The only thing is that in face you have other challenges like expression and then eyeglasses, those kind of issues. Those are not actually in case of ear. So that is why I think there are some implementations where people have tried to do recognition based on ear. But as such, I think wherever face can be used, I think the ear can be can be used. So there's no very exclusive, I think, place. There's another application where I think people are trying to use is like continuous evaluation, continuous authentication when you are making the phone call, let's say. So that case, like when you are keeping your phone near your ear, the continuous kind of uh, authentication can be done. So there's another, maybe we can say that is another, that is one place where uh, we see that we have the use of ear. Yeah.
So there is one more question from Dr. Deepo. How many geometric patterns are there in ears? Any specific number, sir?
Yeah, so you can say theoretically equal to the number of people that are in this earth. Practically, I mean, we don't have a very big database for this. So, for example, I think UND J2 also has, I think, 400 and around 400 subjects. So I think that is the largest database. So biggest study is only on these kind of sample sets. But theoretically, when we are saying that it can be used as a biometric, we expect that every individual has a pattern. So theoretically, the pattern is equal to the number of people that we have in this earth.
Hello.
In, go ahead, madam. Go ahead.
Hello, sir, Karthik, this can is you hear Dr. me? Channamma. Yes, sir.
Hello.
Am I audible?
Yes, yes, madam, you are audible. Please go ahead.
Yeah. Sir, I am Dr. Channamma from JC itself. JC Science and Technology University.
Yeah.
I hope you remember me.
Yes. How are you?
Yes. Sir, I have a question,
Yeah, please.
and that you explained about fake biometrics in the first session.
Mm-hmm.
So, how accurate it is, sir? Say, like fingerprint, maybe using wax, or face, maybe deep fake with respect to face recognition,
I think yes.
and in other gate.
Yes.
So,
Yeah. So I think yeah. So
how
five.
accurately that fake biometrics works, sir? Is it
I think yeah. So
really work?
I think it's quite accurate actually, and it's quite alarming. So, for example,
Oh,
in spoofing in fingerprint has, I mean, even in India, I mean, some cases have been caught. So that is why I think now the companies are creating sensors which are not just capturing your outer pattern, but they are also seeing what is beneath the outer skin. But there are many cases where this has been actually used very successfully. So it's not hypothetical.
and
Even people with the silicon fingerprint, they could actually spoof this system.
yes, sir. Yes, sir. One more is a continuation to that. Is there any work done on identifying fake biometrics? If they use fake biometrics for authentication purpose,
Hmm.
is there any work done on identifying or detecting fake biometric traits?
Mhm. No, so all the work that you see in the domain of a spoof detection is actually all that same thing. So in a spoof detection technique is actually detecting whether the biometric that you are presenting is a spoof or it is a true biometric data, biometric that you are
Yeah,
supplying.
yeah,
Yeah.
yeah.
So the entire domain of the spoof detection is actually that.
Okay. Okay, sir. Thank you.
Yeah.
So there are two more questions here, sir.
Yes, ma'am.
The question is, in women, can we actually go with ear recognition because of changing ear ornaments?
So actually the ear has partial occlusion because of those ornaments, but I think that does not contribute much to the geometry. So though it poses a challenge, but let's say you are using some local features, so it is I mean like maybe only 5 or 10% part of the year that is being occluded. So it doesn't make much difference actually if you are using local features. If you are using global features, then obviously yes, then the performance may be quite poor. But that is
Next
actually only
question
because of
is,
the occlusion. Yeah, I just want to add that this degradation in the performance is happening not because you are using different kind of ornaments, but just because the occlusion is there. Because I mean, whenever the ear is used for recognition, only the ear part is used. Your ornament will be maybe hanging below, right? So that is not creating any problem. But the occlusion that comes because of that attachment is only the problem.
so the question is pattern of both the ears of same person or same or different?
No, they are different actually. There are studies.
Different.
Yeah, if you just search, I mean, your phrase, you will get. There are studies which show that the left and the ear have different patterns.
So Dr. Pratibha wants to know whether the 3D ear data set can be availed for research purpose from IIT Indore.
Yeah, so as of now, actually, we have not formally released it, but I think we are thinking in that direction because I mean, we have got some other requests as well. So maybe uh, soon we will be able to give that for the research.
Any other questions, participants?
Hello.
Can some of you? Yes, sir. Yes, sir. Dr. Shekhar, sir. Yes, sir. Go on,
I have
sir.
question.
Yes,
Good
sir.
evening, sir. Good presentation. I have only one query.
Yes,
Similar to
ma'am.
the finger vein pattern, can we explore ear vein pattern also?
Can you please repeat your question? I could not hear completely.
Similar to the finger vein pattern, vein patterns.
Uh-huh.
Is it
finger vein.
possible to explore ear vein pattern? I mean, is there any research that
Yeah,
is being conducted to look at
yeah.
the
I think
internal details?
yes, yes. I think it's a good point. But as far as I think I know, I have not come across any such work. But I think as
Okay,
a
sir. Okay.
possibility, definitely, I think we can do that.
That's what. If you could have the, I mean, capturing devices are already there, and if you look at the internal structure, maybe
Hmm.
studying the different, taking the data sets of different people,
Yeah, yeah.
obviously they can explore those. That's
Yes,
what I
yes, yeah.
thought, sir.
Yeah, yeah, I
Thought to
think
share with.
yes, yes. I think the theoretically this is, I mean, this seems feasible, but practically, I think we need to see like how well we are able to capture the uh,
Oh,
veins and all that. Because
okay.
I think the way like finger veins are captured, there that is like you have to put your finger inside the device. So you have, I mean, your finger is very close to the device, but here you will be capturing it from a far distance, right? So
Yeah,
I'm not
either
sure.
or else you can something you can use like headphones also we can think of developing such devices and capturing
Ah,
the
so
ear vein pattern.
right, right. So that's why I said so theoretically, yes, I think there is a possibility,
Oh,
but I think till now I don't think anybody has explored this.
thank you very much, sir. We
Yeah.
shall explore
Yes,
after
yes, I
working
think
with you.
definitely. Yeah, yeah. And
I'll write mail.
Good evening, sir.
yes. Yeah, good evening,
Good
madam,
evening,
please.
sir.
Yeah, good evening, madam, please.
Sir, I have one question.
Mhm. Madam, your voice is actually breaking. I think we are not able to
So
hear.
in the first session, you am I audible, sir? No. Am I
No,
audible, sir?
it is
Hello.
better now, but I think your voice is breaking. Yeah, please.
Yeah, sir, biometric data is very important and it needs a lot of security, sir. So,
Mhm.
can I get more information about the visual cryptography? How actually that uh, contributes to this biometric data, sir?
Huh. So I think the Professor Arun Rao's group is very actively working in that domain. So if you just
Okay.
go through his website, I think you will get a lot of information.
Okay, sir. Because basically, I'm from a network security background, so that's
Mhm.
why I'm interested in that topic. Thank you
Okay,
so
okay.
much, sir.
Yeah, but I think that's a good area actually. In the slide also, I think I will be sharing the slides with you all. So in the slide also, you have
Okay,
some
sir.
references. So you can also explore those papers as well.
Okay, sir. Definitely, I will collect.
Yeah.
Thank you, sir.
So, thank you very much, sir. It was very indeed a very, very interesting and informative session. A very good start for the faculty development program on research avenues in biometrics using low cost devices. Sir, it was a great honor to have you in the first session. In the first session, you started with all the basic traits, all the basic information of biometrics, and continuously you took up the ear as a trait, which is very rare and very few work has been taken place across the globe compared to any other traits of biometric. And the second important aspect that you covered is about the descriptors. And I believe that all the participants, whatever the traits they might be using, can also use these descriptors for the traits that they're using over there, especially if you are working on a 3D data set. Sir, we wholeheartedly thank for all your efforts in delivering the talk on the first session. Thank you very much, sir.
Thank you, madam. It was indeed a pleasure. Uh, I really enjoyed the company of you all. Thank you very much for inviting me.
Thank you, sir. Thank you.